Okay, so in this review for this test that we've got coming up on antiderivatives and initial value problems, on most of the basic antiderivative problems, and you'll see this on the next slide in just a second, I've already written down the answers because I don't think you need to see me taking basic antiderivatives. There's one I do want to talk about, but other than that, the answers will already be there, okay? On the problems that I found to be a little bit more difficult, however, I do work through those, and I'll talk about those as we work through the video. So here we go, looking at this review for this test. So on numbers 1 through 6, we're just trying to find the antiderivative of each of these functions. Now, a couple things I want to point out, like on number 3, since that's the sine of 2x, we talked about how to take the antiderivative of something like that when what's causing our composite function is just linear. And remember, we just divide by the derivative of what's in the parentheses, but otherwise we leave it alone. About the only other problem that I wanted to talk about on this was number 5. So I'm going to, on number 5, in order to take this antiderivative, I need to move the x squared up to the top before we take the antiderivative. And again, the reason for that is we don't have some sort of quotient rule, and ln only applies when it's just plain old x on the bottom of a fraction. So now when I take this antiderivative, I'd add 1 to negative 2, so I'd get x to the negative 1, so I'd have 5x to the negative 1 over negative 1. And then the rest of the antiderivative is fairly straightforward. Secant x tangent x, what we took the derivative of to get that was just secant of x, and then we have our plus c on the end. So on number 5, and you could write your answer like that if you wanted to change it to negative 5 over x, that answer's fine too. Either way works. Either way would be correct on this first term here that we took the antiderivative of. But that one is a little bit trickier. Don't forget that if it's not just plain old x, you need to move it up to the top. Now, on a particular solution equation, I know that you could follow, there's two different ways you can do these problems. You can do these problems much how you did particular solutions that had x's and y's mixed together, or you can notice that there are no y's in this equation. So I'm just going to take the antiderivative of both sides and then solve for c. So I take my antiderivative here, and I've got plus c. Then I'm going to plug in 2 for y and 0 for x. So I'm going to get 2 is equal to 0 plus c. So my c in this case is equal to 2. I take that 2 and I plug that back into my original equation, and I get my final answer. Now, if you did this problem where you got the x's to one side and y's to the other, you would have found that this is what you got anyway, just with one additional step where you multiplied dx over to the left-hand side. Either way works. I look at it, and if there's no y's, I just take the antiderivative of both sides. Number 8, we're given the second derivative and asked to find the original equation. So we're going to have to take our antiderivative twice. So I take the antiderivative once, and then I have my plus c. Before I take the antiderivative again, I need to find out what the c is. So you'll notice the dy dx is equal to 10 when x is equal to 1. So I put 10 is equal to 10 times 1 squared plus c. So in this case, my c is equal to 0. That doesn't happen all the time, but in this problem it does. So I get dy dx is equal to 10x squared plus 0. Then I take the antiderivative of that again. When I take the antiderivative again, I get 10x to the third divided by 3 plus c. And this time y equals 4 when x equals 1. So I've got 4 is equal to 10 thirds plus c. If I subtract 10 thirds over, I get 2 thirds as my constant. So the last thing I do is y is equal to 10x to the third divided by 3 plus 2 thirds. Now, this problem, because we started with the second derivative, this problem would not have worked using the method where the x's and y's are mixed together. Or at least it wouldn't have worked on the second derivative. We could have used it here. So that's how we do number 8. Number 9 is very similar. The difference is you'll notice I have a velocity function, and I need to take the antiderivative to get to position. So I take the antiderivative velocity, that gives me s of t equals the antiderivative of e to the t is e to the t. The antiderivative of cosine is sine, so I've got that plus c. Now when time equals 0, s of t equals 4, so I'm going to put 4 there. You got to be careful on this one because I get e to the 0 plus the sine of 0 plus c. E to the 0 is not 0, so I've got 1 plus c is equal to 4. So in this case, I get that c is equal to 3. You do have to be careful when we plug in 0 because it doesn't automatically mean that everything just goes away. So now I get s of t is equal to e to the t plus the sine of t, and then we just found out that c was 3, and that is our final answer for number 9. Now on numbers 10, 11, and 12, all of them are basic antiderivatives. The one thing I do want to kind of call your attention to on number 12 is that's not e to the x, that's e to the negative x. So another way we could have written that term if you wanted to is you go e to the negative x, and then we have 1 multiplied by negative 1 out in front of it. Either way works. Again, that's a simple composite function, but it is a composite function nonetheless. So there's your answers for 10, 11, and 12. If you need to pause it and write those down, that's totally fine. Now on number 13, we're going to start doing u substitution problems. So on number 13, we've got e to the x multiplied by 1 over e to the x plus 4. In this problem, we're going to let e to the x plus 4 be our u. So I've got du dx is equal to e to the x. I also then had the integral of e to the x multiplied by 1 over u dx. So I multiply the dx over and divide by e to the x. I get du over e to the x is equal to dx. I plug that in. I get the integral of e to the x multiplied by 1 over u. Multiply that by du over e to the x, and the e to the x's cancel out. So now I have the integral of 1 over u du. Take the antiderivative of that. I get the ln of the absolute value of u plus c. And then the last step, remember, is just to take our u and plug that back in. So there's your answer for number 13. On number 14, we're going to let u equal x squared. And we're going to put u in for both of the where we see x squared. So I'm going to have the integral of 4x times secant u tangent u. And we've got dx. So now we take the derivative of that. So I get du dx is equal to 2x. With a little bit of manipulation, I get that dx is equal to du over 2x. So I plug that in. I get 4x times secant u tangent u. Then instead of dx, I've got du over 2x. From there, the x's cancel, and 4 divided by 2 is 2, so I have the integral of 2 secant u tangent u du. The 2 can come out in front, so I've got 2 secant u tangent u du. I take the antiderivative of that. The antiderivative of secant u tangent u is secant u plus c. Then I plug my u back in, so I get secant of x squared plus c, and there's my answer for number 14. On number 15, again, since nothing's really in parentheses here that's a composite function, we let u equal the more complicated of the two functions. So in this case, my u is equal to ln of x. So I get du dx equals 1 over x. I know I'm kind of doing these out of order, but I get the integral of u over x dx. And then to get the dx by itself, I'm basically going to cross multiply here. So I get dx is equal to x times du. Once I have that, I've got u over x multiplied by x du. The x's cancel. I've got u du. Take the antiderivative of that. I get u squared over 2 plus c. And then I just plug my u back in. So I get the ln of x squared divided by 2 plus c. So there's my answer for number 15. Again, a little bit more complicated, but not terrible, just that extra steps on u substitution. I'm going to do these ones real quick, and then we can just look at the answers. All right, so on both of these problems, again, you can see how I worked through it. I just want to point out that on 16, we should have let u equal the tangent of x, and on 17, u equals 4x to the third plus 3x squared minus 7. On 16, one way, because there really are two different things in parentheses on number 16, so it's kind of hard to decide what your u is going to be. You kind of sometimes have to think it through, like what is going to cause something to cancel out, and when I take the derivative of tangent, I get secant squared, which is going to make that secant squared of x disappear. So although, again, there's an awful lot of what if going on, you would have known at this step where stuff cancels whether or not you actually did that problem correctly. Hopefully, again, that one kind of makes sense. 18 and 19. Let me do these problems as well real quick. We got a lot of u substitution on this work. Okay, so on both of these problems, especially on number 18, the one thing I want to call your attention to is you let your u equal that x to the third plus 3x squared plus 5. When you get your derivative, you'll notice initially it doesn't look like that's going to cancel with what's on the top. A lot of times what you can do is you look at your derivative and see if there's anything as far as a constant number that you can factor out of both terms. Notice that 3 goes into both of these, so if I rewrote it, I could write it as 3 times x squared plus 2x. That's a big deal because then the x squared plus 2x's will cancel each other out, and then the rest of it we can carry out. The other thing I want to call your attention to is this 1 over u squared. That's not an ln. I need to take the u up to the top by making it u to the negative 2, and then I can take the antiderivative of that. The other thing is on number 19, notice here I've got sine of x and negative sine of x. Negative sine of x is really negative 1 times the sine of x. So when the sine of x is canceled, I can pull this negative 1 out in front. It's like negative 1 over negative 1. Because it was technically on the bottom. That still gives you negative 1. Then you can take the antiderivative like you normally do. So that's how we get through 18 and 19. Now in numbers 20 and 21, I already drew the slope fields for you. Don't forget, to find a slope field, you just take the points and you plug them in one point at a time, and you find the slope at that point and you draw it. So both of these are just slope fields based on, that was a pretty easy idea. On these ones, remember, what we're looking for is I want to find out where we have a 0 slope repeatedly and where we have an undefined slope. So on this one, number 22, it looks like at x equals negative 3, there's a 0 slope. And then an undefined slope, it looks like there's one at, that one's actually looks like it's about 2.5, to be honest, is where that 0 slope looks to be. Y equals 2.5, okay? More or less, it might be 2. Well, we'll go with 2, actually. It looks more like 2.5, but we'll go with 2. So remember, in order to have a 0 slope, whatever's on top of the fraction has to equal 0. In order to have an undefined slope, whatever's on the bottom of the fraction, when I put that in, has to equal 0. So there is my derivative for that one. Now on number 23, I've got y equals 1 as a 0 slope, y equals negative 2 as a 0 slope, and x equals, looks like positive 1 as an undefined slope. So this one's going to be y minus 1 and y plus 2 on the top, because those are my 0 slopes. And on the bottom, I get x minus 1, and that is equal to our derivative. So that's how we do 22 and 23. Now, number 24, what we want to do is we want to find the original function. This one I'm going to do using separation of variables. So everything that has an x, we're moving over to the left-hand side, or to the right-hand side. Everything that has a y, we're moving to the left-hand side. So I've got this right here. You could do it the way that we did the first couple problems if you want, but I want to focus on this method. Now remember, once we get the y's to one side and the x's to the other, we take the antiderivative. So I get y is equal to x to the third minus 2x squared plus c. Then we find our c, so I plug in 2 is equal to 1 cubed minus 2 times 1 squared plus c. So that's 1 minus 2 plus c is equal to 2. That's going to give us that c is equal to 3. Normally what we do, and we do this on this problem as well, is we take that c and we plug it back in. Now normally on these problems, what we do is now we'd have to get the y all by itself. In this problem, the y is already by itself, so we are done with number 24. And you would have found that same answer if you'd used the same technique that we used earlier. On number 25, however, we can't use that technique. Instead, we need to multiply the 2y over to the left-hand side, and we need to multiply the dx over to the right-hand side before we take the antiderivative. So when I do that, I get y squared is equal to x to the third divided by 3 plus x plus c. Now we're going to find our c by plugging in 2 and 0. So I get 0 cubed divided by 3 plus 0 plus c. So c is equal to 4. So I've got y squared is equal to x to the third divided by 3 plus x plus 4. Then to get the y by itself, I take the square root of both sides. So I get x to the third divided by 3 plus x plus 4. And then we look at our y value, see how it's a positive number, to determine whether or not this is positive square root or negative square root. In this case, because that number is positive, that means that is what my y is going to be equal to, the positive version of that equation. Hopefully most of these made sense. I know this was a little bit longer review, but antiderivatives are pretty important. So if you have any questions about this or anything else, please let me know.